next talk. So the speaker will be Nicholas Hunter-Jones. He's from Parameter Institute, and he will talk about models of quantum complexity growth. Hi, Nick. Can you share the screen?
Hi. Yeah, so you can hear me?
Yes.
Great. And I'll just share screen.
Okay, so before you start, I wanted to remind all the speakers that so the talk is for 30 minutes, and there will be 15 minutes per discussion after that. And I will give you a reminder about the 5 minutes. Okay. You can start when you're ready.
Okay, you can see my screen right now?
Yes, I can.
All right, excellent. Hi. So first, I'd like to thank the organizers, Vedika, Tianxi, Sagar, and Tom, for putting together this very interesting workshop, kind of at the intersection of quantum many-body physics, condensed matter, and quantum information. And of course, for inviting me to speak. And I'd like to thank all of you for being here despite the circumstances. So I'm going to be talking today about complexity growth. Oh, and feel free to interrupt, I guess, if there's a short question throughout the duration of the talk, but I guess we'll have a lot of time for questions at the end. So I'm going to be talking about two papers, both of these papers from last year. The first was with Fernando Brandao, Wissam Chamasani, Richard Kung, and John Preskill. And in this paper, we studied kind of models of complexity growth and tried to basically exactly compute the complexity for a number of models, including random quantum circuits. And in proving some of our main results, we used basically some results from a paper from last year about the randomness generated by random circuits. So I'll say more precisely what that means. And I should mention that a lot of the ideas and techniques that were developed in this paper were due to Richard Kung, who's pictured here, who's now at Johannes Kepler University in Austria. So let's get started. So today we'll be interested in quantum complexity, which is a pretty fundamental and well-established notion in quantum information, and it kind of allows us to distinguish computational tasks which are easy versus hard for a quantum computer. But the quantum complexity of a state has kind of come up a lot more recently in quantum many-body physics, where kind of computing the complexity of certain ground state wave functions has been used to distinguish topological phases of matter. And more recently, in the context of the ADS-CFT correspondence, the complexity of a specific CFT state has been conjectured to describe the region behind an ADS black hole. But I think much more generally, and probably of much more interest to this audience, I think we believe that complexity growth is sort of one universal aspect of quantum many-body systems, and specifically in their real-time dynamics. So, if you take some strongly interacting many-body system and like ask for different universal features, I think complexity growth is one of these phenomena, along with things like thermalization, quantum chaos, scrambling, entanglement growth, or operator growth. And kind of understanding how all these things are connected is maybe a long-term goal of this subject. But today we'll just be interested in quantum complexity. And complexity is a pretty intuitive notion, where the traditional definition involves constructing a circuit with gates drawn from some universal gate set, which we pick at the beginning, which approximately implements some state or some unitary. So approximately prepares that state or unitary to within some tolerance, okay? And we are then interested in the minimal size of the circuit which does this, which can be constructed from this gate set and to within that tolerance, okay? So I'll define this more precisely in a little bit, but maybe just to fix some notation. In this talk, I'll be considering systems of n qubits. So n will be the number of qubits, and the local dimension will be q, such that the total dimension is going to be d, which is obviously q to the n. Okay, so d is the total Hilbert space dimension. Okay, so it's believed, or possibly conjectured, that the complexity of a simple initial state, so some not so entangled state, grows possibly linearly under time evolution by a chaotic Hamiltonian. So we have this long time linear growth, which saturates after an exponential time. And this expectation extends to the time evolution operator itself. So it's believed that the complexity of the operator e to the IHT also grows, possibly linearly, for some chaotic Hamiltonian H, saturating at some time scale, which is like e to the n, or again, n is the number of qubits. So, this might sound reasonable, but the problem is actually analytically computing or lower bounding the quantum complexity is extremely hard, especially for some fixed h, because, say you actually find some circuit which is constructed from your two local gates or your universal gate set, which approximates your unitary time evolution. What you then need to do is prove that it's the minimal such circuit, right? So this task sounds very daunting because naively it sounds like we need to enumerate all possible, circuits to find the minimal one. Okay. But first, let's just think about why we expect these different features, this linear growth and this saturation. So roughly speaking, the complexity should scale with the time we evolve for, and kind of collisions, so shortcuts at sub-exponential time should be rare. So we might expect this linear growth. And we can also find upper bounds on the complexity growth from different Hamiltonian simulation algorithms. So taking your unitary time evolution operator, decomposing it, trotterizing and maybe decomposing into two local gates, and then bounding the total error. Right, we might be able to construct some circuit which approximates this this evolution operator, right, and that will be an upper bound on the complexity. So I think different Hamiltonian simulation algorithms tell you that this growth should be at most polynomial in T. And then why do we expect this saturation region? Well, we can simply just count count the number of unitaries in the unitary group. So what we find is just by counting balls of size delta in the unitary group, you observe that there are doubly exponential distinct unitaries. So there's something like 1 over delta to the 2 to the 2n distinct unitaries, so delta balls in the unitary group. So if we think about the number of circuits of depth, of some depth, we realize that once the circuit depth reaches something exponential, so like 2 to the n, we notice that the number of possible circuits of that depth and the number of unitaries in the unitary group are roughly equal, right? So what that's saying is we can reach any unitary to within some tolerance delta with an exponential depth circuit. So this is why we expect the complexity to saturate at some late time. Right? But these are all expectations. What we actually want to do is set out try and set out and prove something. So to make progress, there are a few different things you can do. One thing you might imagine doing is making some complexity theoretic assumptions to make statements about the complexity of some specific Hamiltonian construction at very late times. So this is what was done by Aronson, Susskind, as well as Bogdanovich and Brandow, where they assumed, some reasonable complexity theory assumption like p space doesn't equal, BQP or something, to show that the complexity at of a particular Hamiltonian needed to be super polynomial at exponentially long times. So this kind of makes progress in addressing this late time regime. But one thing we can do to make progress in actually proving something about this growth regime is to, instead of focusing on a specific Hamiltonian, is to focus on ensembles of time evolutions. And in the spirit of the last talk, the ensemble I'm going to be interested in is the ensemble of random quantum circuits. Okay, so just as Matthew nicely explained, we know we can consider these random quantum circuits on n qubits of local dimension q. And one of the models I'm going to be considering is this evolution by staggered layers of two-site unitaries. So we act on even links at even time steps and odd links at odd time steps. And where each unitary is drawn randomly from a gate set G. Okay, so we have randomness in space and time. And where evolution to time t is given by a depth t circuit, which is the product of t layers. Okay, and our goal is going to be to prove something about the growth of complexity for this model. Yeah, I should say that the actual circuit geometry isn't going to be too important for the first part of this talk. So here we have this, nice brickwork random circuit. But we could also consider these local random circuits where at each time step we act with one gate, which is chosen randomly on some random neighboring pair of qubits. And of course, the only difference is that we apply order n gates here per time step, and here we just apply one. So the scaling in time is scaling in times for these two models will differ by a factor of n. But kind of the distinction between these isn't actually that important right now. And I find it a little bit more convenient to talk about the depth of the circuit instead of size. So T here will be the depth of the circuit, right? So the number of layers. Okay. Are there any questions about anything so far? Right. So, right, the goal is to prove something about complexity in these models. And a priori, it sounds kind of simple. Sorry, was there a question?
I need to there's a question.
Yeah, please.
Daniel, you can unmute and ask the question.
Okay, I can just ask directly. Yeah, so I was just wondering if it matters that initially you've been speaking about time-independent Hamiltonians, so you're looking at the time evolution e to the IHT,
yep.
And now you're considering random circuits, which are time-dependent Hamiltonians.
Absolutely, yeah. I think this is what we would call a tactical retreat. So I would love to be able to compute something about the complexity for a fixed time-independent Hamiltonian, but I don't know how to. So we're talking about time-dependent evolution, and specifically an ensemble of time-dependent evolutions, because that's kind of the regime where we can compute things. But I would say maybe the long-term goal is it would compute the complexity for a fixed time-independent Hamiltonian.
Sure. Yeah, I was wondering in comparison to ensembles of time-independent Hamiltonians, but I guess you answered the question.
Yeah. So you can. I'm going to talk about basically the ensembles called designs, and there's a reason why even ensemble of time-independent Hamiltonians might be a little tricky for this approach. But maybe ask your question again at the end of the talk, and I'll have a more interesting answer, or I'll have something else to say.
Thanks.
Okay.
Nick, I have a brief
follow-up. Please.
So here you're thinking about complexity of states evolved by these circuits, not of the operators themselves, the time evolution operators.
Actually, that's thank you for getting me to clarify that. I'm actually going to be talking about the complexity of the unitary itself. Basically, all the results we can say for states as well, but at least just for a 30-minute talk, it's a little bit easier just to talk about the unitary. It's pretty easy to translate all the same statements to statements about states. But yeah, I'll just be talking about the complexity of unitaries.
Thanks.
Right, so naively, this question seems pretty simple. I give you a random circuit, say we pick these gates randomly from G, and that's also the gates that we define complexity with. It seems like this, this circuit should I just count the gates and that should be my complexity. But again, the issue is, that is a unitary which approximately prepares your unitary. But what you need to do is prove that it's the minimal one, right? So even given some circuit like this, how do you prove that you couldn't have approximately prepared that unitary with a shorter circuit? And that's really the difficulty here. Okay, so specifically, it's been conjectured that most local random circuits of depth t have a complexity which scales linearly in time for an exponentially long time. And this sounds totally reasonable, but again, as I emphasized, this is hard to prove because you kind of need to show that collisions between circuits of small size are rare. And that these collisions need to dominate as the circuits get, exponentially deep. Okay, so first I'm going to define the complexity of a unitary, and then we're going to prove some results about the complexity of very nice ensembles called unitary designs. And then we'll turn back to random circuits and, kind of prove something about their complexity growth. And then in the last part of the talk, we're going to basically prove that random circuits generate randomness as rapidly as possible, and that'll allow us to prove the conjecture. Okay. So as I said, we're considering a system of n qubits, local dimension q, and where the total dimension is d. And as I said, the complexity of a unitary is the minimal size of the circuit built from those two local gates, which approximates the unitary. So here we might define some universal gate set G of two local gates. And we're going to let G sub R denote the set of all circuits of size R. Okay. And then more formally, we're going to say that a unitary has some complexity of at most R if there exists a size R circuit such that those two unitaries are close. And for formal reasons, I have some fancy metric I'm using for what I mean by close. This is something called the diamond norm between the channels. But it's not so important. It's just kind of a nice measure of distance between two unitaries. Okay, and what this, what this says, if this is true, then we'll say that the unitary has complexity of at most R, and then we're interested in finding the minimal R for which this is true. And actually, in our paper, we use a slightly stronger definition of complexity in terms of kind of the complexity of an optimal distinguishing measurement. And I'm not going to really mention this for the rest of the talk, but I should mention that quite a bit of work went into proving all of our results for this stronger definition of complexity. But everything I'm going to say holds for both the standard circuit complexity as well as this kind of complexity of measurement, where roughly the strong complexity of a unitary is the minimal circuit required to implement some Ensemble-assisted measurement capable of distinguishing the channel from the completely depolarizing channel. And this definition is stronger in the sense that something can have high complexity under this definition and low complexity under this stronger definition. But that's all I'm going to say about that. Okay, so we're interested in the complexity of random circuits. And to make progress, I want to derive some very general statements about the complexity of nice ensembles called unitary designs. But first, I obviously need to tell you what a unitary design is. So as you might know, the Haar measure is the unique left and right invariant measure on the unitary group. So this is really what we mean by a uniform measure on the unitary group. And we can define something called a k-fold channel. It's kind of this like conjugated action by k-fold operators. So we say that the k-fold channel with respect to the Haar measure on the unitary group of an operator O is this average over the Haar measure. And so say we might be interested in when averages over the full unitary group look like averages over some subset. We can consider some ensemble of unitaries, so some discrete, some set of points on the unitary group. We then say that the k-fold channel with respect to that ensemble is is similarly defined like this, as this average over the ensemble. And we'll say that this ensemble of unitaries looks like averages over this ensemble of unitaries look like averages over the full unitary group if these k-fold channels are equal for all operators O. So more precisely, what we're going to say is an ensemble of unitaries is an exact k-design if the k-fold channels are equal for all operators O. So this is a little technical, but really what we're saying here is we have this big unitary group. We're averaging maybe over the kth moment. And when do those averages over the kth moment exactly look like some average over a set of points? Okay, is there some set of points where if we average over those, it looks like an average over the full unitary group up to the kth moment? So that's what an exact k-design is. And more importantly, these ensembles exist. So for k equals 1, Pauli operators form an exact 1 design. But in general, even though we know these constructions exist, very little is known. So we only know up to the third moment these exact constructions. So for general k, we can kind of relax our definitions a little bit and ask when an ensemble is close to looking like the unitary group, is close to being Haar random. So an approximate k-design is an ensemble where these k-fold channels are close in this diamond norm. And designs are actually very powerful in quantum information because there are all these really nice results you can get from them, and that's because they kind of allow you to wield the power of the full unitary group with relatively low complexity. So it's always nicer to explain things with pictures. So again, just to reemphasize, we say an ensemble of unitaries forms an approximate k-design if the average over that ensemble is close to the average over the full unitary group up to the kth moment. Right? So the average over like this set of points, is close to this average over the full unitary group for k copies of U and U dagger. And that's what an approximate k design is. And maybe a little bit more intuition for a k design. We can ask how random the time evolution of a system is compared to the full unitary group. So if you consider some ensemble of time evolutions at a fixed time t, so this could be, as we're considering, random quantum circuits, or maybe some Brownian circuit, or even time evolution generated by disordered Hamiltonians. Right? This is some set of unitaries at some time. At time equals 0, right? This is just a bunch of points sitting at the identity. But chaotic time evolution is going to move us rapidly and ergodically over the unitary group. So we can imagine, quantifying the randomness of this ensemble of time evolutions by asking at what times does this system form a k design, and start approximating moments of the unitary group. At what times does it look very random? Okay, so that's what a k design is. They're really nice ensembles. And what we might imagine asking is, if we take some approximate design, just does the statement that it forms a design, this set of unitaries forms a design, allow us to prove anything about the complexity of the elements of that ensemble? And the answer is yes. Basically, the structure of a design is pretty restrictive, and you can prove these two statements, which I've just given here informally. You can prove that with extremely high probability, a unitary drawn from an approximate design, so this ensemble, has complexity roughly n times k. Okay, so with very high probability for a k design, the complexity of an element is roughly n times k. And moreover, we can go in and explicitly count the number of unitaries of a given complexity. And what you find is that there are e to the nk distinct unitaries of this complexity. And the emphasis on distinct is important here because we're basically trying to bound collisions. Right? So this is saying, kind of on average, if you with extremely high probability, if you draw an element from this ensemble, it'll have this complexity. And moreover, we can go in and explicitly count the number of unitaries with this complexity, and there's an exponential number of them. And they're distinct. Okay? And distinct is, again, important because we're trying to bound collisions. Okay, so I'll just give the more formal statement. The statement you can actually prove under both of these definitions of complexity is that an approximate unitary design contains at least this many distinct unitaries with complexity at least r, which is essentially this is essentially e to the nk. Okay, so that was a statement about complexity of designs. But we're interested in random circuits. So if we consider these G-local random circuits on n qubits, we can use this very powerful result from Brandau, Harrow, and Horodetsky, which says that the set of all, this ensemble of G-local random circuits of depth t, forms an approximate unitary design if the depth is greater than this. So this is a little bit messy, but roughly what this is saying is that random quantum circuits of depth n times k to the 11 form k designs. Okay, so that just means if we evolve for long enough, these random circuits will start, approximating moments of the unitary group, and then we can use this previous result to say something about their complexity. So combining these two theorems, what we can show is that we can make these two statements about the complexity of random circuits. And we can say that with extremely high probability, exponentially close to 1, a local random circuit of depth t has complexity n times t to the 1 over 11. I should just say roughly t times t to the 1 over 11. And the set of depth t random circuits contains at least this many distinct unitaries of this complexity. Okay, so this establishes some polynomial relation between the growth of complexity and the depth of the circuit up to very late times. Right, so this is this slow kind of t to the 1 over 11 growth. But what we really set out to do was prove a linear growth. Okay, so this allows us to prove, some slow growth, but what we really wanted was a linear growth. So I'll just recap, kind of this complexity by design result, what we've shown is that complexity is linearly related to the design order K. And then what we used was this nice result that random circuits formed designs where T is roughly, K to the 11, or T is order K to the 11. And this gave us that the complexity is related to T with this exponent. Okay. But kind of more importantly, you can just use this result for any time-dependent model or any kind of model of any kind of evolution which forms designs. So you can use this design growth result and just start plugging in other results. So for example, it's known that Brownian quantum circuits, so this is kind of like a two-local spin model with random couplings, time-dependent couplings. It's known that they form designs in a depth which is like K to the 11. And this gives, again, the same slow complexity growth. There's a nice, there's a very nice nearly time-independent construction from Nakata et al., where they showed for this kind of slightly time-dependent Hamiltonian that you form K designs linearly in K, but only up to basically K equals square root n. So this gives a short time complexity growth, which is linear in T. And lastly, it's known that higher dimensional random circuits, so this would be random circuits on some capital D dimensional lattice, form designs with some very high exponent K. So this gives a very slow sublinear complexity growth. But what we were really interested in was the linear growth for these random quantum circuits, these 1D random quantum circuits. And as I said, to get a linear growth in complexity, you need a linear growth in design, right? So we had this linear relation between complexity and design order K. And to prove a linear, linear growth in complexity in time, what you need to prove is a linear relation between T and K, right? So we had from this result, from this Brandahera-Hordetsky, we had that T equals K to the 11. But what we need is that T is, something like order NK. And moreover, a lower bound on the K design depth for random quantum circuits is known. It's known to be linear in NK. So what you really need to do is prove that random circuits saturate this lower bound and are thus optimal implementations of designs. So kind of even tying into the last talk even more, what you can do is you can use this exact statistical mechanical mapping. And what you can show is that random circuits form K designs in this optimal depth in n times K depth. If you take basically a large local dimension. So the statement is that random circuits on n qubits, local dimension Q, form unitary designs when the circuit depth is T equals n times K for some local dimension Q where this Q naught will depend on the size of the circuit. So you do need to take it to be large. Right. So again, we're considering, these random circuits, and we're asking when, how fast do they converge to unitary designs? And I'll just, basically in the last few minutes mention how the statistical mapping allows you to compute this. So what you can do is you can focus on the 2 norm and analytically compute a quantity called the frame potential for random circuits. And you make use of some very nice ideas in these 2 papers by, two of our organizers, and what it allows you to do is write the frame potential exactly as a lattice partition function, and you can compute this partition function exactly for K equals 2, but in general you need to sacrifice some precision. But there's a very nice interpretation of the decay to Haar randomness in these random circuits that can be understood in terms of domain walls, very similar to as Matthew just described. So very briefly, the frame potential is sort of just another measure of Haar randomness, another measure of how close you are to forming a design. And it's defined as, for any ensemble of unitaries, where the kth frame potential is just given as this double average over the ensemble. And for any ensemble, it's lower bounded by its Haar value of K factorial, with equality if and only if you form a design. So for some K and some set of unitaries, some ensemble of unitaries, this is just some number you can compute, and how close that number is to K factorial tells you how close you are to forming a design. Okay? So it's just kind of a really nice measure of Haar randomness. And the goal is just to compute this quantity now, where the ensemble is random circuits of depth T. So doing the Haar averaging and writing and kind of using this mapping, as was described in the previous talk. For this case, in circuits with no measurements, right, these are just pure unitary evolution. The mapping in this case allows you to write this frame potential exactly as the partition function on a triangular lattice, where the local degrees of freedom are elements of the symmetric group Sk. So, it's kind of a Potts model in the sense, or a k factorial degrees of freedom per site, where the lattice has width n over 2 and depth 2t, and with periodic boundary conditions in time. So these spins here identified with these spins here, and that identification basically comes from the trace here. So periodic boundary conditions in time. And where these plaquette terms are functions of 3 spins, which you can write explicitly as this funky expression, but it's just some function you can compute. And what you can show is that if you plug in the same spin everywhere, you just get a weight of 1. So in that sense, you can see where this minimal Haar value comes from. It comes from the k factorial ground states of this lattice model. And so, everything else that contributes to this partition function are just excited states, which must decay as we approach kind of, Haar randomness, as we approach this minimal value. So it turns out that all non-zero contributions to this partition function are domain walls, which must wrap the circuit. So here's an example of a single domain wall configuration or a double domain wall configuration. And to compute the k-design time, you just basically need to count these domain walls. And for k equals 2, basically, you can exactly do that. You can just exactly compute, basically, by solving some random walk problem, you can compute kind of these combinatorial coefficients. And that allows you to extract the depth at which you form a 2 design.
Yeah. Can you summarize?
Yeah, absolutely. I only have like 2 more slides, so don't worry. I'll wrap up in like 2 minutes, 1 minute. So, right, and that allows you to compute the 2 design depth, which is linear in n, which is known. And this basically is just solving the problem using some nice stat-mech methods of p non-intersecting random walkers. But for general k, you need to sacrifice some precision, and it turns out you can basically compute the ground states and the first excited states. And then by taking a large Q limit, what you can do is show that all the further excited states are suppressed. And this allows you to compute the design depth from the single domain wall sector, and what you find is that it's linear in n and k. Okay? So the result is that random circuits form k designs in this kind of optimal depth if you take large Q. And I think there are a number of reasons why this large Q limit might not be necessary. But for the purposes of this talk, what this allows us to conclude is to establish the conjecture for random circuits, at least in the limit of large local dimension. So what this shows is that, again, the depth t is linear related to the design order k. And what that means is that local random circuits of depth t have complexity t. And moreover, the set of all random circuits of depth t contains at least an exponential number in t distinct elements of this complexity. So what that says is complexity is growing linearly in time for a long time. And the number of unitaries with that complexity, generated in this case by time evolution to time t, so depth t random circuits, is exponential. So there's an exponential number of these distinct high complexity unitaries. Okay, and that's everything I wanted to talk about. There are a lot of future directions, but I guess I'm a little bit over time, so I'll just end here. And if anyone wants to ask about these things, well, please do. So thanks for listening.
All right, thank you. It's a very solid talk, solid nice results. So let's see if we have questions. So if you have a question, you can either type in the chat or you can raise your hand, and I will ask you to mute and read out the question. If no one is asking, you can just unmute yourself. Please. Okay, let me first maybe ask a naive question. So you have proved that for random circuit, so the complexity grows as n times k. So that's an ensemble random circuit. So, but presumably, if you take a subset of that ensemble, it also will not have too much collision, I imagine, because you don't have collision for the whole ensemble. And so, does that entail any results for the subset?
I guess it depends, like what subset you're thinking about. So, yeah, if your subset is something like Clifford circuits, I would say that kind of well, we know that they don't form Clifford circuits don't form designs. Basically, that you can only get up to 3 designs. So yeah, in that case, no. But maybe yeah, I would expect that if you do something like a generic. So let's say obviously the orthogonal group is a subgroup of the unitary group. So if we were to pick our gates from the orthogonal group, I would expect that basically all these results would also be true, but probably also some generic subset of these circuits. All these results should also hold, but it might be hard to actually.
So basically, if you impose a discrete symmetry, it doesn't affect too much.
Oh, I see. Yeah, I would expect that. So I think the route you would need to go. I think it shouldn't affect these results that much. I think you should also get like this long time complexity growth, and the route you would probably need to go to prove it, because I think if you start imposing these symmetries, they won't form designs. So here, the route we took was we knew that this very nice ensemble called the design. We could prove complexity about that ensemble. And then what we needed to do was just show that random circuits form designs, and then we were done. But if you impose some symmetry, I think on the random circuits, like you choose the gates from some smaller subset, maybe maybe these charge conserving circuits or some kind of other symmetry you impose locally. I think then they wouldn't form kind of these full designs. They would form. You'd need to modify your definition of a design. So there's probably some maybe for these charge conserving circuits, there might be a notion of a design where you're kind of random within these like charge sectors. So probably what you need to do is then prove the complexity result for that kind of modified definite, maybe symmetric design or something, and then then you need to prove that random circuits form those symmetric designs, and then I think that would give you the result you would need. But yeah, I guess I think that should work out.
All right. So there are more questions in the chat. So Thibault, can you unmute yourself?
Yeah, sure. So my question was, thanks for a very nice talk, by the way.
Yeah.
But my question was, is there any known connection between entanglement and complexity? Something like, if I know that my state has an area law entanglement, does that put some upper bound on the complexity it can have?
Well, yeah. So I mean, you say entanglement. I think maybe what you actually mean is like entanglement. And so yeah, everything is entanglement, right? Everything here is like this long time complexity growth is basically one hidden aspect of entanglement that you couldn't see just from entropies, right? So basically, I would say that we know that kind of all of these entropies saturate at a pretty early time. So I think entanglement entropy for these random circuits roughly saturates at a time that's like order n. And I think you can show that basically all Rennies, there's a formal way to basically prove that all Rennies saturate at a time scale which is like n or n squared or something. So all of the entanglements are basically maximal at a time scale which is way before complexity saturates. So somehow complexity growth is entanglement. It's just some aspect of entanglement that you couldn't see from entropies. So if you're asking like what that is, I don't know how to define it other than complexity.
Well, my question was basically how big can this difference be in the sense that, let's say I say that the entropies have an area law, so they're very small in some sense.
Yeah.
Does that mean that then the complexity can be at most polynomial, or can it still be exponential?
Yeah, that's a good question. In short, I don't know. Like I think my intuition is the best for these kind of very chaotic systems, and maybe like if you're thinking about states, maybe states that have this kind of volume law entanglement. I guess I would expect that for kind of for systems which evolve generic states to sort of maximal entanglement, I would expect that they would have this long time complexity growth. The converse, I'm much less confident in saying. I don't know if you have some area law entanglement, something which generates area law entanglement, if you could prove anything or say anything concrete about the complexity needing to be submaximal or a lot slower or something. Yeah, I don't know. It's a good question.
Yeah, thanks.
Okay. Next question is from Matthew. Matthew, can you unmute yourself?
Yeah, hey, great talk. I'm not sure if this is a well-defined question, but let me try it. you're considering in some situations the large local Hilbert space dimension to Q, and proving some things which, if Q is large enough, do you require that Q scales with a number of qubits?
With n, yeah, basically, I think actually the most severe thing is that I think I only require it scale with k. Yeah, basically I can improve on the results I just mentioned a little bit, and I think, yeah, I don't see a way of not getting it to scale with k. I think you can make it n independent, but I think you still, it's like k here is the design order. So I think what I can prove is that you get this linear growth as long as you take q larger than k squared. So that's n independent, but it's still dependent on k.
Okay,
so technically, and maybe this is what you're getting at, I wanted to, and I kind of swept this under the rug a little bit. I wanted to prove this, extremely long time complexity growth up to like exponential times, and that's like a time scale that's like d. And really, I still have some restriction. Really, I'm taking q to be large, right? So that doesn't really allow me to, I can, as long as I take q large enough, I can prove this linear complexity growth. But I'm never really going to be able to prove it all the way up to d timescales if I have this large q limit, right? Because I'm taking q to be large in a way that, the dimension becomes larger. So I think to really, we proved is this linear growth and complexity, but I think you really need to just, yeah, it would be amazing if we could just prove this for like q equals 2, and then prove that it's linear growth all the way up to like, 2 to the n, which is like your Hilbert space dimension d. But yeah, the only things I know how to do are basically prove this if you take q to be larger than k squared.
thank you.
Yeah.
So just follow up. So this you can only prove within a short range of time because your result is valid for q greater than some t dependent.
That's right. I mean, it depends what you're calling short times. If you take, I mean, it's definitely not, it's not, the time scale you'd like to be able to go up to is q to the n. Yeah, what you're doing is you're proving this up to something which is q dependent. If you take q large enough as some large fixed value, you get a linear growth up to that value. So you can take n to be extremely large and q to be, so you can get past n timescales if you take q large enough. But I agree, this is a little bit unsatisfying. You really want a linear growth that's completely independent of all the parameters in the problem.
All right.
Yeah.
Next question. Abena, can you unmute yourself? Hello, am I pronouncing it?
Hello, can you hear me?
Yep.
Yeah. So my question was whether you can. So it's probably in a similar sense as the previous one. So you mentioned this result that there's the linear time of linear complexity growth until square root time. I think that was from some result you cited. I hope I couldn't get that. So I was wondering if you can bootstrap that to get something for longer times. And so one way this could, so one way this could be done.
Was it this model you were talking about?
Right. That's right. Yeah. So one way this could be done is like if you could extend this result to the case of advice. So yeah, there's probably like some sense in which the one giving you the advice tells you like an optimal.
It's giving you what?
Advice.
Okay. Yeah.
So they can give you like the optimal circuit for up to time t, and then maybe you want to extend this result for t plus square root n or something like that, and then you keep doing that.
Yeah. So I mean, this is a different model than these random circuits I was considering. So I was just kind of, in this talk, I mostly focused on random circuits, as I mentioned before. But basically, if you have any time evolving model which forms designs, you can just kind of plug this into the one of the results we had and prove something about the complexity growth. So this is a different kind of Hamiltonian time dependent, or it is a time dependent Hamiltonian construction. And yeah, you're right that here they give this kind of linear short time growth, but I don't know if there's any simple way of kind of bootstrapping this to later times. There were nice techniques used in this paper, but yeah, I don't know if this would inform anything about longer time random circuit complexity growth. And even if you just wanted to improve this result, I don't know if there's necessarily a clear way forward, but it's probably true that this linear growth persists in this model for kind of later times.
Okay, I see. Thanks.
Yeah.
All right. Oh, I guess we have still 1 minute. Maybe Tom, you can ask your question.
Yeah, my question was, so in cases where the complexity grows slower than linear in time, so I guess at late times, or I think you mentioned in higher dimensions, I was wondering from like a quantum simulation perspective, I guess one, does this imply that you could simulate the unitary with a lower depth quantum circuit? And if
so I think, yeah, really this is a question of, yeah, that's a good question. So maybe I'll just keep one of these plots up. So yeah, the ones, I would say that basically for these random circuits and this linear growth, you're really allowed to say that you've proved complexity is growing linear because you have like an upper bound and a lower bound, which are both just like t. I would say that for these other things, it's really that you have a lower bound on the complexity, which is sublinear.
I see.
So, and then an upper bound, which is maybe like t squared, or maybe t.
Okay.
So instead of like, I wouldn't take that as evidence. I mean, it could be like this is the true behavior, and that like slower growth is saturated, and thus like, and that would have implications for quantum simulation, right? Because if that lower bound is saturated, then that means that the complexity really is something faster than you thought it was. But I would be more inclined to say that I would expect that if you like just worked harder and were able to improve, like if I were able to improve some of these results, like for these other models, what you would really find is that like the upper and lower bounds like saturate for this linear in time.
Okay.
Instead of this like, yeah. So the slow growth is probably just like a lower bound, and probably it can be improved to linear.
Okay, so you would guess that things generally continue growing linearly, even where you can't prove it.
Yeah, basically, it would be nice if you could improve, like one clear way to prove linear complexity growth is basically improve these design results. So it's basically a statement for these design results, you get this high polynomial power of k. And if you could improve that k dependence, then that would improve this complexity result. But I think, yeah, probably generally for most many-body systems, for most chaotic many-body systems, this linear growth is probably pretty universal.
Okay.
But, I mean, obviously, I can't prove that
Sure.
than for random circuits.
Okay, thank you.
Yeah, thanks.
All right. Thank you very much. So let's thank the two speakers, Matthew and Nick. Very nice talk.